Hello, in this lecture we'll answer two questions. The first question, we'll find out the area of this green shape that is inside square TSQP. And the second question, we'll find out the area of this green shape that is inside square ABCD. So we'll start with the first question. In the drawing we have two squares. We have the big square TSQP and the small square ABCP. In addition, we know that the area of this triangle AMP is equal to 9 square units in its size, and the area of this quadrilateral ABCP is equal to 27 square units in its size. Again, our task is to find out the area of this ring shape. So first of all, we know that the area of the small triangle ABCP in total is equal to 9 plus 27, that is 36 square units in its size. So I write it down. The area of this small right triangle ABCP, and the area of this small square ABCP is equal to 36 square units in its size. The area of square ABCP total is equal to 9 plus 27, that is 36 square units in its size from one side, but from the other side we know that the area of any square equals to the length of one side squared. Again, the area of any square is equal to the length of one side squared. So the area of this small square ABCP will be equal to the length of side AP squared. This is AP squared. So from one side, the area of square ABCP is equal to 27 plus 9, that is 36 square units in size. From the other side, the area of square ABCP equals to one side squared, that is AP squared. From this equation, we will derive that AP squared equals to 36. Here, we'll take a look at this equation, and we get that AP equals to the square root of 36, that is 6. So AP equals to 6 units in its length. This is side AP is equals to 6 units in its length. You know that all the angles inside the square, are right angles. So in square ABCP, this angle must be equal to 90 degrees in its side. It is 1 out of 4 angles inside square ABCP. Therefore, it is equal to 90 degrees in its size. It's given us the question that the area of this right triangle AMP is equal to 9 square units in its size. So the area of this triangle AMP on one side is equal to 9 square units in its size. But from the other side, we know that the area of any triangle equals to the base of the triangle, that is AM, times the height, that is AP, over 2. Then again, from one side, the area of this right triangle AMP is equal to 9 square units in its size. But from the other side, the area of this right triangle AMP equals to the base AM times the height AP over 2. From this equation, AM times AP over 2 equals to the area for the right triangle AMP equals to 9. We will derive that AM times AP over 2 equals to 9. We have already found out that AP equals to 6, so we substitute here AP by 6, and we get that AM times AP to the 6 over 2 equals to 9. 6 over 2 is 3, so in total this expression equals to 3 AM. So 3 AM equals to 9. Here we divided the equation by 3, and finally get that AM equals to 9 over 3, that is 3 units in its length. This is side AM, that is equals to 3 units in its length. In the next step, I'll copy the right triangle AMP in a new page, and we will implement on this right triangle AMP the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the evolution for Pythagoras theorem. So this is the right triangle AMP, that is according to the original domain. This right triangle AMP, MP squared, that is the square of the hypotenuse, equals to MA squared plus AP squared. So I write it down. MP squared, that is the square of the hypotenuse, equals to AM squared plus AP squared. MP is the missing side, so we leave it as it is. So it is MP squared equals to AM squared. AM is 3, therefore AM squared is 3 squared, that is 9, plus AP squared. AP is 6, therefore AP squared is 6 squared, that is 36. So in total, MP squared equals to 9 plus 36, that is 45. So MP squared equals to 45. Here we will substitute 45 by 9 times 5, and we get that MP squared equals to 9 times 5. Here we take a root out of this equation, and finally get that the length of the hypotenuse MP is equal to the square root of 9, that is 3, over, so inside the root we have to only be 5. So in total we found out that MP, the length of the hypotenuse MP, is 3 times square root of 5 units in its length. This is the hypotenuse MP is equals to 3 times square root of 5 units in its length. We know that TSQP is a square, and all the angles inside the square are right angles. Therefore, this is the right angle. There is 1 out of 4 angles in square TSQP, therefore it is a right angle. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this angle S alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. So in the small right angle TMB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. Likewise, in this big right triangle A and P, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that those two right angles are similar to each other, but before that, what is the length of side MB? MB equals to AB minus AM. So already know MB equals to AB minus AM. So MB in total equals to AB 6 because in square AB CP all the sides are equal to each other, each side equals to 6. So MB 6 minus AM is 3. So in total MB equals to 6 minus 3, that is 3. So MB equals to 3, it's in its length. MB equals to 3, it's in its length. This is the side MB, that equals to 3, it's in its length. It is very easy to see that the small right triangle TBM is similar to the big right triangle AMP. So why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, both those two angles are both equal to alpha and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So we should find out that all the angles in the big right triangle AMP are corresponding equal to all the angles in the small right triangle TMB, and therefore those two right triangles are similar to each other according to angle similarity rule. So already now we actually found out that the big right triangle AMP is similar, this is the sign of similar, to the small right triangle TMB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the big right triangle AMP over side TB of the small right triangle TBM equals to side AM of the big right triangle AMP over side TM of the small right triangle TMB, and it is also equal to side MP of the big right triangle AMP over side MB of the small right triangle TMB. Then again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle AMP over side TB of the small right triangle TMB is equal to side AM of the big right triangle AMP over side TM of the small right triangle TMB, and it is also equal to side MP of the big right triangle AMP over side MB of the small right triangle TMB. AP 6 over TB. TB is the missing side, so leave it as it is. And it is equal to AM. AM is 3 over TM. TM is the missing side, so leave it as it is. And it is also equals to MP. MP is 3 times square root of 5 over MB. MB is 3. So in total, we shall find out that six over TB equals to 3 over TM equals to 3 times square root of 5 over 3. We have 3 in the numerator, 3 in the denominator, so 3 will get cancelled, and we left only with square root of 5. So 6 over TB equals to 3 over TM equals to square root of 5. Those two sides are equal to each other, so we can the first equation from those two sides that are equal to each other. So 6 over TB equals to square root of 5. Here we will multiply this equation by TB and then we divide it by square root of 5 and we get that TB equals to 6 over square root of 5 units in its length. So actually this is side TB that equals to 6 over square root of 5 units in its length. Those two sides are equal to each other, so we get the second equation from those two sides that are equal to each other. So here we get that 3 over Tm equals to the square root of 5. 3 over Tm equals to the square root of 5. Here we will multiply this equation by Tm and then we divide it by square root of 5 and we get that Tm equals to 3 over square root of 5 units in its length. This is the missing side of Tm. This is equals to 3 over square root of 5 units in its length. Our task is to find out the area of this grain shape. So, what is the area of the grain shape? On the drawing, it is very easy to see that the area of this grain shape equals to the area of the big square TSQP minus the area of this quadrilateral MBCP minus the area of this small right triangle TMB. So, write it down. If you found out that the area of this grain shape equals to the area of the big square TSQP minus the area of this quadrilateral MBCP minus the area of this small right triangle TBM. Again, the area of the grain shape in total equals to the area of the big square TSQP minus the area of quadrilateral MBCP. The area of this quadrilateral MBCP equals to 27 square units in its size according to what is given in the question, minus the area of this small right triangle TMB minus the area of the small right triangle TMB. So, what is the area of the big square TSQP? So in order to find out the big square TSQP, we have to find out the length of side TP. That is one side, a square TSQP. So what is the length of side TP? TP in total equals to TM plus MP. Again, TP in total equals to TM plus MP. So TP equals to TM plus MP. So TP in total equals to TM is 3 over square root of 5, plus MP equals to 3 times square root of 5. So in total, the length of side TP of the big square TSQP equals to 3 times square root of 5 plus 3 times square root of 5. Again, TP equals to 3 over square root of 5 plus 3 times square root of 5. So TP equals to 3 over square root of 5. Here we will multiply this number 3 times square root of 5 by square root of 5, and then we divide it by square root of 5. And we get that square root of 5 times square root of 5 is 5, and 5 times 3 is 15 over square root of 5. We multiply it by square root of 5, and then we divide it by square root of 5. So we change nothing because it is allowable to multiply anything by 1. So TP in total equals to 3 plus 15, that is 18 over square root of 5. So TP in total equals to 18 over square root of 5 units in its length. And again, we should found out that the length of side TP, that is one side of square TSQP, in total it is equal to 18 over square root of 5 units in its length. TP in total equals to 18 over square root of 5 units in its length. So what is the area of the big square TSQP? We already found out that the area of the big square TSQP equals to the length of one side squared. That is to say, the length of TP squared. So the area of square TSQP is equal to TP squared. That is, the area of any square equals to the length of one side squared. So it is TP squared minus the area of quadrilateral MPCP. The area of this quadrilateral MPCP. The area of this quadrilateral is 27 square units inside according to what is given as the question. So it is minus 27 minus the area of the small right triangle TBM. The area of this small right triangle TBM equals to the base TB times the height TM over 2. So it is equal to the base TB times the height TM over 2. So in total, the area of the green shape equals to the area of square TSQP, that is TP squared. TP is 18 over square root of 5, and therefore TP squared is 18 times square root of 5 squared. Minus 27, that is the area of quadrilateral MBCP, minus the area of the small right triangle TBM, that is equals to TB. TB is square root times square root of 5, 6 over square root of 5, times TM. TM is 3 times square root of 5, divided by 2. And again, in total, the area of this small right triangle TMB is equal to the length of side TB, that is 6 times square root of 5, times the length of it is the height, the base TB, that is 6 times square root of 5, times the height TM, that is 3 over square root of 5, divided by 2. So we have here the area of square TSQP equals to 18 over square root of 5 squared. 18 over square root of 5 squared is equal to 18 squared, that is 324, over square root of 5 squared, that is 5. Minus 27, and here we have 6 times 3 is 18, and 18 over square root of 5 times square root of 5 is 5, and 5 times 2 is 10. So in total, the denominator we have 10. So in total, the area of the small rectangle TBM equals to 18 over 10 square units in its size. So the area of the green shape in total equals to 324 over 5 is 64.8 square units in its size. That is the area of the big square TSQP. Minus 27 and minus 18 over 10 is minus 1.8. So here we have 64.8 minus 1.8 is 63, and 63 minus 27 is 36. So in total, we should find out that the area of this green shape, that is the area that you are looking for in this question, is equal to 36 square units in its size. Repeat again, we should find out that the area of the green shape equal to 36 square units in size. The area of this green shape is equal to 36 square units in its size. So we finish with the first question. In the next step, I will present you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the area of this green shape that is inside square ABCD. So in the drawing we have square ABCD. We know that one side of square ABCD equals to 10 units in size, therefore all the other sides must also equal to 10. In addition, we know that inside this square ABCD we have this semicircle. The diameter BC of this semicircle is 10, and therefore the radius must be equal to 10 over 2, that is 5. We define the center of this semicircle. This point is point O. So the radius OB equals to 5, and the radius OM, the radius OC also equals to 5. That is the radius of the semicircle. We know that point A is the center of the quarter circle. So inside this square we have this big quarter circle. Point A is the center of the quarter circle. Point B is the point of the quarter circle itself. Therefore AB is the radius of the quarter circle, that is equal to 10. Likewise, AD is also the radius of the quarter circle, that is equal to 10 units in its length. In the next step, we'll define the intersection point between the quarter circle and the semicircle. This point is point M, and we will join points A and M together by a straight line. Point A is the center of the quarter circle, point M is the point on the quarter circle itself, therefore AM is the radius of the quarter circle, is equal to 10. AM is actually a tangent to the semicircle at point M. Again, AM is a tangent to the semicircle at point M. In the next step, we will join points O and M together by a straight line. Point O is the center of the semicircle, point M is the point on the semicircle itself, therefore OM is the radius of the semicircle, that is 5. So here we can implement rule 1. Well, because we have the radius OM of the semicircle that is equals to 5, the radius OM is drawn to point M, that is the point of tendency of tangent AM with this semicircle. And remember, you have radius that is drawn to the point of tendency, then tangent AM will be perpendicular to the radius MO, according to rule 1. So if AM is perpendicular to MO, it means that this angle equals to 90 degrees. We know that all the angles inside the big sphere ABCD are right angles, and therefore this is angle ABC, this is a right angle. So in the next step, we'll join points A and O together by a straight line. By joining points A and O, we can deal two right angles. This is the right angle AMO, and this is the right angle AOB. In the next step, we'll prove that those two right angles can go into each other according to side rule. So, already known, we'll prove that the right angle AOM can go to the right angle AOB according to side rule. So why those two right angles can go into each other? First of all, side OB of the right angle ABO is equal to side OM of the right angle AOM. They're both the radii of the semicircle that is equal to 5, and therefore they are equal to each other. So OB equals to OM equals to 5. Repeat again. Side OB of the right angle AOB equals to side OM of the right angle AOM. They are both equal to 5. They are both the radii of the circle that is equal to 5, and therefore they are equal to each other. In addition, side AB of the right angle AOB equals to side AM of the right angle AOM. They are both the radii of the quarter circle that is equals to 10, and therefore they are equal to each other. So AB equals to AM equals to 10. Repeat again. Side AB of the right angle AOB equals to side AM of the right angle AOM. They are both the radii of the quarter circle that is equals to 10, and therefore they are equal to each other. And finally, this is side AO, that is a common side that belongs to both angles. So you can find out that AO equals to itself is a common side that belongs to both angles. So I can prove that all the three sides of the big right angle ABO corresponding equal to all the three sides of the big right angle AOM, and therefore those two right angles can go into each other according to side rule. So I write it down. I can find out that the right angle AOB congruent, this is the sign of congruent, to the right angle AOM according to side rule. And from the fact that those two right angles can go into each other, we derive that those two angles are also equal to each other. Those two angles are equal to each other according to the rule that corresponding angles and congruent angles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other. So if we find the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. Likewise, from the fact that those two right angles can go into each other, we derive that those two angles are also equal to each other according to the same rule that corresponding angles can go into angles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to the rule that I mentioned. So in the right triangle AOB, the sum of the angles must be equal to 180 degrees. So which angles we have in the right triangle AOB? We have alpha plus beta plus 90 degrees, in total must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. And again, in the right triangle AOB, the sum of the angles must be equal to 180 degrees. So alpha plus beta plus 90 degrees equals to 180 degrees. Here we subtract 90 degrees from this equation, and we get that alpha plus beta equals to 180 degrees minus 90 degrees. 180 degrees minus 90 degrees is 90 degrees. So alpha plus beta equals to 90 degrees. Here we subtract alpha from this equation, and we get that beta equals to 90 degrees minus alpha. We continue to focus on this right triangle ABO. So in the next step, I'll copy the right triangle ABO in the new page, and we will implement the Pythagoras theorem on this right triangle ABO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the information for Pythagoras theorem. So actually, this is the right triangle ABO that I copied from the original drawing. In this right triangle ABO, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. So AO squared equals to AB squared plus BO squared. AO is the missing side, so we leave it as it is. So it is AO squared equals to AB squared. AB is 10, therefore AB squared is 10 squared, that is 100, plus BO squared. BO equals to 5, and therefore BO squared equals to 5 squared, that is 25. So in total, AO squared equals to 100 plus 25, that is 125. So AO squared equals to 125. Here we'll substitute 125 by 25 times 5, and we get that AO squared equals to 25 times 5. Here we'll take a root out of this equation, and finally we get that AO, the missing side AO, equals to the square root of 25, that is 5. So inside the root we left only with 5. So in total we should find out that AO equals to 5 times square root of 5 units in its length. This is side AO. This is equals to 5 times square root of 5 units in its length. We continue to focus on this right triangle ABO. In the right triangle ABO, sinus alpha equals to BO over AO. And again, in the right triangle ABO, sinus alpha equals to BO over AO. So sinus alpha equals to BO. BO is 5 over AO. AO is 5 times square root of 5. So in total, we found out that sinus alpha equals to 5 over 5 times square root of 5. We have 5 in the numerator, 5 in the denominator, so 5 will get cancelled, we left only with 1 over square root of 5. So in total, we found out that sinus alpha equals to 1 over square root of 5. Our task is to find out the value of angle alpha itself. In order to find out the value of angle alpha itself, we'll operate on the result, that is, the result of sinus alpha is 1 point over square root of 5, so we will operate on the result, the opposite side of sine, that is arc sine. In this way we get the value of angle alpha itself. So arc sine, that is the opposite function of sine, of the result of sinus alpha is 1.1 over square root of 5. It will get us the value of angle alpha itself. And arc sine of 1 over square root of 5 is equal to 26.565 arc sine of 1 over square root of 5. Total, it is equal to, the angle alpha equals to 26.565 degrees. Again, if we found out that angle alpha itself equals to 26.565 degrees. And therefore 2 alpha must be equal to 2 times 26.565. That is actually 53.13 degrees. So if we found out that 2 alpha equals to 53.13 degrees. This is the big angle 2 alpha. This equals to 53.13 degrees. We already found out that beta equals to 90 degrees minus alpha. So write it down, and we found out that beta equals to 90 degrees minus alpha. So beta equals to 90 degrees minus alpha. And alpha equals to 26.565 degrees. 90 degrees minus 26.565 is equal to 64.345. But again, angle beta equals to 64.435 degrees, and therefore 2 beta must be equal to 2 times 64.435 degrees, that is actually 126.87 degrees. 2 beta equals to 126.87 degrees. This is the big angle 2 beta. The big angle 2 beta is actually angle BOM is equal to 126.87 degrees in its size. So our task is to find out the area of this green shape. So in order to find out the area of this green shape, we will join points M and B together by a straight line. By joining points A and B, we divided the green shape into 2 parts. The first part is the upper segment we define the upper segment BUM. This is the upper segment BUM. And the second part is the lower segment. This is the lower segment. So we define the lower segment as segment BLM. This is the lower segment BLM. So by joining points B and M together by straight line, we divided the green shape into two parts. The first part is the segment BUM, the upper segment BUM, and the second part is the lower segment BLM. So we'll calculate the area of each segment separately, and then we'll add the two areas together, and this will be the area of this green shape. In order to find out the area of the lower segment BLM, I'll copy this sector ABM. In an equation, we will analyze this sector ABM. This is angle 2 alpha. This is equals to 53.13 degrees. AB equals to 10, AM also equals to 10. They are both the radius of the quarter circle. This is equals to 10. So actually, this is sector ABM, that I call it from the original drawing. So what is a sector? A sector is a portion of a circle with two radii, AB and AM, this is the radius of the quarter circle, and the arc that enclosed between the two radii. And again, the green shape AOB is a sector. You can see that it is a portion of a circle with two radii, that are the radii of the circle, and the arc AB that is enclosed between the two radii. So this is sector AOB. The two radii AO and BO are defined as the legs of the sector. So the angle between the legs of the sector AO and BO is theta. So the area of this sector AOB equals to the area of the circle that contains the sector, that is pi r squared, times the angle between the legs of the sector, that is theta, over 360 degrees. But again, the area of this green sector AOB equals to the area of the circle that contains the sector, that is pi r squared, times the angle between the legs of the circle, that is theta, over 360 degrees. So we use this new formula in order to find out the area of this sector AOB. According to the formula that I presented to you, the area of this sector AOB must be equal to pi r squared. This is the area of the circle that contains the sector. R is the radius of the quarter circle, that is 10, times the angle between the legs of the sector, that is 53.13 degrees, over 360 degrees. R is the radius of the quarter circle, that is 10. Therefore, r squared is 10 squared, that is 100. So pi r squared is 100 pi. times 53.13 over 360 degrees. In total, the value of this expression, 100 pi times 53.13 over 360 degrees. In total, the value of this expression is actually equal to 46.3646. 46.3646 square units in its size. So if you found out that the area of this sector ABM, in total it is equal to 46.3646 square units in its size. Our task is to find out the area of this lower segment BLM. And again, our task is to find out the area of this lower segment BLM. This is the lower segment BLM that we have to find out the area of it. So, what is the area of the lower segment BLM? For the long, it is very easy to say that the area of this lower segment BLM, in total it is equal to the area of the big sector ABM minus the area of triangle ABM. Repeat again, the area of the lower segment BLM in total equals to the area of the big sector ABM minus the area of triangle ABM. It is very easy to see from the drawing that if you remove from this sector ABM the triangle, you will get segment BLM. Therefore, the area of segment BLM equals to the area of sector ABM minus the area of triangle ABM. We have already found out that the area of the big sector ABM equals to 46.364 units in its size minus the area of triangle ABM. The angle between AB and AM is 53.13 degrees. AB equals to 10. AM also equals to 10. So in the next step, I will present to you a new formula that will help us to find out the area of any triangle. This is triangle ABC that could be any triangle. In triangle ABC, side AB equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta. So, according to the new formula, the area of this triangle ABC that could be any triangle equals to A times B, that is the multiplication of two sides by each other, times sinus the angle between the two sides, that is sinus theta, divided by 2. Repeat again. The area of this triangle ABC that could be any triangle equals to A times B times sinus theta over 2. So we use the new formula in order to find out the area of this triangle ABM. According to the new formula, the area of this triangle ABM equals to AB times AM, that is the multiplication of two sides by each other, times sinus the angle between the two sides, that is sinus 53.13 degrees, divided by 2. And again, the area of the triangle ABM equals to AB times AM times sinus the angle between the two sides, that is 53.13 degrees, over 2. So the area of this triangle ABM in total equals to AB is 10 times AM is also 10, so 10 times 10 is 100 times sinus 53.13 degrees. Sinus 53 0.13 degrees is equal to 0.8 divided by 2. 100 over 2 is 50, and 50 times 0.8 is 40. Again, 50 times 0.8 is 40. So in total, we found out that the area of this triangle ABM is equal to 40 square units in its size. So the area of the lower segment BLM equals to the area of the sector ABM, that is 46.36 square units in its size, minus the area of this triangle ABM, that equals to 40 square units in its size. 46.3646 minus 40 equals to 6.3646 square units in its size. So in total, we actually found out that the area of the lower segment BLM, the area of this lower segment BLM equals to 6.3646 square units in its size. And again, the area of this lower segment BLM equals to 6.3646 square units in its size. So the next step, we will find out the area of the upper segment BUM. In order to find out the area of this upper segment BUM, I'll copy sector OBM. This is sector OBM that I'll copy in a new page, and we analyze this sector OBM. The angle between the legs BO and OM is equal to 2 beta. That is equal to 126.87 degrees in its size. BO or OB is the radius of the semicircle, that is 5. OM is also the radius of the semicircle, that is equal to 5. So actually, this is sector OBM that I covered from the original drawing. The area of this sector OBM, according to the formula that I presented to you a couple minutes ago, the area of this sector OBM equals to pi r squared, that is the area of the circle that contains the sector. R is the radius of the semicircle, that is 5. So it is pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 126.87 degrees over 360 degrees. R is 5, therefore you can see that R equals to 5, and therefore R squared is 5 squared, that is 25, so pi R squared is 25 pi times 126.87 degrees over 360 degrees. In total, the value of this expression, 25 pi times 126.87 over 360, in total it is equal to 27.678 square units in its size. 27.678 square units in its size. So in total, we should find out that the area of this sector OBM equals to 27.678 square units in its size. Our task is to find out the area of the upper segment BUM. Our task is to find out the area of this green segment BUM. Upper green segment BUM. So what is the area of the upper segment BUM? This is the upper segment BOM. Right. This is the upper segment BOM. Exactly like this segment BOM. So what is the upper segment BOM? The upper segment BOM. In total, the area of this upper segment BOM must be equal to the area of the big sector OBM. And we already found out that the area of the sector OBM equals to 27.678 degrees in its size, minus the area of triangle OBM. This is triangle OBM. This is triangle OBM. The angle between side BO and OM is 126.87 degrees. BO equals to 5. OM also equals to 5. And according to the formula that I presented to you, the area of this triangle BOM will be equal to BO times OM times sinus 126.87 divided by 2. BO is 5, OM is 5, so BO times OM is 5 times 5, that is 25, times sinus 126.87. Sinus 126.87 degrees is 0.8 divided by 2. 25 over 2 is 12.5, and 12.5 times 0.8 is 10. So in total, we should find out that the area of this triangle BOM equals to 10 square inches in its size. And in total, the area of this upper segment BOM equals to the area of sector BOM, that is actually 27.678, minus the area of triangle BOM, that is 10. 27.678 minus 10 is 17.678 square inches in its size. So in total, we should find out that the area of this upper segment BOM equals to 17.678 square inches in its size. So the area of this upper segment BOM equals to 17.678 square inches in its size. Our test is to find out the area of this green shape. The area of this green shape equals to the area of the upper segment BOM, that is 17.678 square inches in size, plus the area of the lower segment BLM, that is equals to 6.3646 square inches in size. So the area of the green shape in total equals to the area of the upper segment BOM, that equals to 18.678 square inches in its size, plus the area of the lower segment BLM, that equals to 6.3646 square inches in its size. So repeat again, we should find out that the area of the green shape in total equals to the area of the upper segment BOM, that equals to 17.678 square inches in size, plus the area of the lower segment BLM, that equals to 6.3646 square inches in size. And 17.678 plus 6.3646 is equal to 24.0426 square units in its size. And again, I should find out that the area that we are looking for in this question, that is the area of this green shape, in total it is equal to 24.0426 square units in its size. So in the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our test was to find out the area of this green shape. So, in the domain, we have two squares. We have the big square TSQP and the small square ABCP. In addition, we know that this is triangle AMP is equals to 9 square units in size, and this is quadrilateral MBCP. This is equal to 27 square units in size according to what is given in the question. Again, our test is to find out the area of this green shape. So first of all, we focus on this small square ABCP. The area of this small square ABCP in total is equal to 27 plus 9, that is 36 square units in size. So the area of the small square ABCP in total it is equal to 27 plus 9, that is 36 square units in size from one side, but from the other side, the area of any square equals to the length of one side squared. And therefore the area of this square ABCP will be equal to the length of side AP squared, that is AP squared. So from one side, the area of the small square ABCP is equal to 36 square units in size, but from the other side, it is also equal to the length of one side squared, that is AP squared. It is AP squared. From this equation, AP squared equals to the area of the small square ABCP equals to 36. We'll derive that AP squared equals to 36. Here we'll take a root out of this equation and find out that AP equals to the square root of 36, that is 6. So this is side AP, this is side AP, that is equals to 6 units in its length. In the next step, actually we know that all the angles inside the square are right angles. So all the angles inside this square ABCP are equal to 90 degrees, and therefore this is a right angle. So in the right triangle AMP, we know that the area of the right triangle AMP equals to 9 square units in size. So from one side, the area of the right triangle AMP equals to 9 square units in size, but from the other side, the area of the triangle AMP is equal to the base AM times the height AP over 2. Okay, again, from one side, the area of the right triangle AMP equals to 9 square units in size according to what is given in the question, but from the other side, the area of the right triangle AMP equals to the base AM times the height AP over 2. From this equation, AM times AP over 2 equals to the area of the right triangle AMP equals to 9. We will derive that AM times AP over 2 equals to 9. AP equals to 6, so we can substitute AP by 6. We get that AM times 6 over 2 equals to 9. 6 over 2 is 3, so in total this expression equals to 3 AM equals to 9. If we divided this expression by 3, I should find out that AM, the missing side AM equals to 9 over 3, that is 3. So this is side AM, this is equals to 3 units in its length. In the next step, I copied the right triangle AMP in a new page and implemented the Pythagoras theorem in this right triangle AMP. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. So this is the right triangle AMP that I copied from the original drawing. Side AM equals to 3, AP equals to 6. AP, the hypotenuse, is the missing side. So according to the Pythagoras theorem, AP squared, that is the square of the hypotenuse, equals to AM squared plus AP squared. MP is the missing side, so it is this, so it is MP squared equals to AM squared. AM is 3, therefore AM squared is 3 squared, that is 9. plus AP squared. AP is 6, therefore AP squared is 6 squared, that is 36. So in total, MP squared equals to 9 plus 36, that is 45. So MP squared equals to 45. Here we took a root out of the equation, and I found out that before that, we substituted 45 by 9 times 5, so MP squared equals to 9 times 5. Here we took a root out of the equation, and I found out that MP equals to the square root of 9, that is 3. Inside the root we left only with 5. So in total MP equals to 3 times square root of 5 units in its length. Okay, this is side MP, this is equals to 3 times square root of 5 units in its length. We know that all the angles inside this big square TSQP are right angles, and therefore this is a right angle. So those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. So in the small right triangle TBM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in this right triangle AMP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the sum rule that said that the sum of the angles in any triangle is equal to 180 degrees. Those two triangles are similar to each other according to angle similarity rule. So why the small right triangle TBM is similar to the big right triangle AMP? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, both those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if you found out that all the angles in the big right triangle AMP are corresponding equal to all the angles in the small right triangle TMB, and therefore those two right triangles are similar to each other according to angle similarity rule. So if you found out that the right triangle AMP is similar, this is the sum of similar to the right triangle TMB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the big right triangle AMP over side TB of the small right triangle TMB equals to side AM of the big right triangle AMP over side TM of the small right triangle TMB, and it is also equal to side MP of the big right triangle AMP over side MB of the small right triangle TMB. And again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the big right triangle AMP over side TB of the small right triangle TMB equals to side AM of the big right triangle AMP over side TM of the small right triangle TMB, and it is also equal to side MP of the big right triangle AMP over side MB of the small right triangle TMB. What is the length of the missing 9 element MB? MB equals to AB. MB equals to AB minus AM. Again, MB equals to AB minus AM. We know that all the sides in square ABCP are equal to each other. AP equals to 6, and therefore AB also equals to 6. So AB is 6 minus AM. AM is 3. So in total, MB equals to 6 minus 3, that is 3. So MB equals to 3 units in its length. So we found out actually that AP over TB equals to AM over TM equals to MP over MB. AP is 6 over TB. TB is the missing side, so reality it is, and it is equals to AM. AM is 3 over TM. TM is the missing side, so reality it is. And it is also equals to MP. MP is 3 times square root of 5 over MB. MB is 3. So to that, we should find out that 6 over TB equals to 3 over TM equals to 3 times square root of 5 over 3. We have 3 in the numerator, 3 in the denominator, so 3 will get cancelled, we left only square root of 5. So in total we should find out that 6 over TB equals to 3 over TM equals to square root of 5. Those two sides are equal to each other, so we get the first equation from those two sides that are equal to each other. So 6 over TB equals to the square root of 5. 6 over TB equals to the square root of 5. Here we multiplied this equation by TB and then we divided by square root of 5 and we found out that TB equals to 6 over square root of 5 units in its length. This is side TB, this equals to 6 over square root of 5 units in its length. Those two sides are also equal to each other, so we get the second equation from those two sides that are equal to each other. So according to the second equation, 3 over Tm equals to the square root of 5. 3 over Tm equals to the square root of 5. Here we multiplied this equation by Tm and then we divided by square root of 5. And we actually found out that Tm equals to 3 over square root of 5 units in its length. This is side Tm, this is equal to 3 over square root of 5 units in its length. What is the length of TP? It is one side of the big square TSQP. TP in total equals to Tm plus MP. And again, TP in total equals to Tm plus MP. So TP equals to Tm. Tm is called 3 over square root of 5. Again, Tm is 3 over square root of 5 plus MP. MP is 3 times square root of 5. Again, MP is 3 times square root of 5. So in total we should find out that TP equals to 3 over square root of 5 plus 3 times square root of 5. So here TP equals to 3 over square root of 5 and we multiply 3 times square root of 5 by square root of 5 and then we divide it by square root of 5 in order to overcome a factor with this number. By multiplying anything by 1, we don't change the value of this expression, so it is allowable to multiply it by square root of 5 and then we divide it by square root of 5. So 3 square root of 5 times square root of 5 is 5 and 5 times 3 is 15. So in total the numerator we have 15 divided by square root of 5. So TP equals to 3 plus 15, that is 18 over square root of 5. So I should find out that the length of one side of this big square TSQP is equal to TP, and TP equals to 18 over square root of 5 units in its length. And TP equals to 18 over square root of 5 units in its length. Our task is to find out the area of this range shape. So what is the area of this range shape? From the drawing it is very easy to see that the area of this range shape equals to the area of the big square TSQP minus the area of this quadrilateral MBCP is equal to 27 square units in its size according to what is given in the question, minus the area of this small rectangle TMB. And again, the area of the range shape in total is equal to the area of the big square TSQP minus the area of quadrilateral MBCP is equal to 27 square units in size according to what is given in the question, minus the area of the small rectangle TBM. So the area of the big square TSQP equals to the length of one side TP squared. So it is TP squared. The area of the big square TSQP equals to TP squared minus the area of quadrilateral MBCP. The area of this quadrilateral MBCP is equal to 27 square units. So it is minus 27 minus the area of the small rectangle TMB. This is the small rectangle TMB. The area of this small rectangle TMB equals to the base TB times the ITM over 2. And again, the area of this small rectangle TMB equals to the base TB times the ITM over 2. So we have the area of the big square TSQP, that is TP squared. TP is 18 over square root of 5, and therefore TP squared is 18 over square root of 5 squared minus 27, and TB is called 6 over square root of 5 times Tm, that is 3 over square root of 5 divided by 2. 18 over square root of 5 squared equals to 18 squared, that is 324 over 5 squared, that is 5 minus 27, and we have here 6 times 3 is 18 over square root of 5 times square root of 5 is 5, and 5 times 2 is 10. So in total the numerator we have 10. So in total this expression equals to minus 18 over 10. So the area of the green shape in total equals to 324 over 5. 324 over 5 is 64.8 minus 27, and minus 18 over 10 is minus 1.8. 64.8 minus 1.8 is 63, and we have 63 minus 27 is 36. So in total, we should find out that the area of this green shape, that is the area that we are looking for in this question, is equal to 36 square meters in size. Repeat again, the area of this green shape equals to 36 square meters in size. So we finish with the first question. In the next step, I present you to the second question, and we solve the second question of this lecture. Our task in the second question is to find out the area of this green shape. So in the drawing we have the big square ABCD. We know that one side of this square ABCD is 10, therefore all the other sides are equal to 10. In addition, we know that inside this square ABCD we have this semicircle. The diameter BC of the semicircle is 10, therefore the radius must be equal to 10 over 2, that is 5. So the radius O is the center of the circle. So the radius OB is 5, the radius OC is also 5. And inside this square we have this big quarter circle. Point A is the center of the quarter circle. Point D is the point of the quarter circle itself. Therefore AD is the radius of the quarter circle, that is 10. So in the next step we define the intersection point between the semicircle and the quarter circle. This point is point M, and we join points A and M together by straight line. Point A is the center of the quarter circle, point M is the point of the quarter circle itself, therefore AM is the radius of the quarter circle, that is equal to 10. In the next step we join points O and M together by straight line. Point O is the center of the semicircle, point M is the point of the semicircle itself, therefore OM is the radius of the semicircle, that is 5. We have AM. What is the definition of line segment AM? AM is tangent to the semicircle at point M. So AM is a tangent, and we have the radius OM of the semicircle, that is equal to 5. The radius OM that is equal to 5 is drawn to point M, that is the point of tendency of tangent AM in this semicircle. And whenever we overdo that is drawn to the point of tendency, then tangent AM will be perpendicular to the radius OM. So if AM is perpendicular to OM, according to 1, it means that this angle equals to 90 degrees. Again, if AM is perpendicular to OM, it means that this angle equals to 90 degrees, according to rule 1. You know that all the angles in square ABCD are right angles, and therefore this is a right angle. In the next step, we join points A and O together by straight line. By joining points A and O, we can get those two right angles. We have the right angle ABO and the right angle AMO. So in the next step, we prove that those two right angles can go into each other according to side rule. So when those two right angles can go into each other, first of all, side BO of the right angle AOB equals to 5, and side OM also equals to 5, and therefore they are equal to each other. In addition, side AB of the right angle AOB equals to side AM of the right angle AOM. They are both the radii of the quarter circle, that is equal to 10, and therefore they are equal to each other. And finally, side AO is the common side that belongs to both angles, so we can write down that AO equals to itself is the common side that belongs to both angles. So in total, we should find out that all the sides of the right angle ABO corresponding equal to all the sides of the right angle AOM, and therefore those two right angles can go into each other according to side rule. But again, we should find out that the right triangle AOB congruent, this is the sign of congruent, to the right triangle AOM according to side rule. And for the fact that those two right angles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles and congruent angles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. Likewise, from the fact that those two right angles can go into each other, We realize that those two angles must be also equal to each other according to the sum that corresponding angles in congruent angles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other. So if you define the size of this angle is better, then the size of this angle must be also equal to better, because they are equal to each other according to the rule that I mentioned. Note that all the angles inside any triangle are right angles. So the right triangle ABO, alpha plus beta plus 90 degrees must be equal to 180 degrees. And again, the right triangle ABO, according to the rule that the sum of the angles in any triangle equals to 180 degrees, we get that alpha plus beta plus 90 degrees equals to 180 degrees. Here we subtract the 90 degrees from this equation, and we found out that alpha plus beta equals to 180 degrees plus 90 degrees is 90 degrees. Alpha plus beta equals to 90 degrees. Here we subtract alpha from this equation, and we found out that beta equals to 90 degrees minus alpha. So this is angle beta, this equals to 90 degrees minus alpha. In the next step, I copied the right triangle ABO in the new page and implemented the Pythagoras theorem on this right triangle ABO. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Actually, this is the right triangle ABO, this is the from the original domain. This right triangle ABO, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO is the missing side, so we leave this it is. So it is AO squared equals to AB squared. AB is 10, therefore AB squared is 10 squared, that is 100, plus BO squared. BO is 5, therefore BO squared is 5 squared, that is 25. So in total, AO squared equals to 100 plus 25, that is 125. So AO squared equals to 125. Here we substitute 125 by 25 times 5, so AO squared equals to 25 times 5. Here we took out of this equation and found out that AO equals to the square root of 25 is 5, and inside the root we left only with 5. So in total we found out that AO equals to 5 times square root of 5 units in its length. This is side AO, this is equal to 5 times square root of 5 units in its length. We will continue to focus on the right triangle ABO. The right triangle ABO, sinus alpha equals to BO over AO. Again, in the right triangle ABO, sinus alpha equals to BO over AO. BO equals to 5 and AO equals to 5 times square root of 5. AO equals to 5 times square root of 5. Again, BO equals to 5 and AO equals to 5 times square root of 5. We have 5 in the denominator, 5 in the denominator, so 5 gets cancelled, and we left only with 1 over square root of 5. So in total we should find out that sinus alpha equals to 1 over square root of 5. Our test is to find out the value of angle alpha itself. In order to find out the value of angle alpha itself, we'll operate on the result of sinus alpha, that is 1 over square root of 5, the opposite function of sine, that is arc sine, and we get in this way the value of angle alpha itself. So the opposite function of sine is arc sine, so we operate it on the result of sinus alpha, that is 1 over square root of 5, and in this way we get the value of alpha itself. So arc sinus 1 over square root of 5 is equals to alpha, and alpha equals to 26.565 square units in its size. Alpha equals to 26.565 square units in its size. Therefore, 2 alpha must be equal to 2 times 26.565, that is 53.13 degrees. Again, alpha equals to 26.165 degrees, and therefore 2 alpha equals to 53.13 degrees. We have already found out that beta equals to 90 degrees minus alpha. Here, beta equals to 90 degrees minus alpha. So beta equals to 90 degrees minus alpha, and alpha equals to 26.565 degrees. 90 degrees minus 26.565 degrees is 64.345 degrees. So total we should know that beta equals to 64.135 degrees, and therefore 2 beta equals to 2 times 64.435 degrees. This is 126.87 degrees. So 2 beta equals to 126.87 degrees. This is the big angle in MOB, this is equals to 2 beta. 2 beta equals to 126.87 degrees, and this is the big angle MAB, this is equals to 2 alpha, and 2 alpha equals to 53.13 degrees. Our test is to find out the area of this grain shape. In order to find out the area of this grain shape, we join points M and B together by straight line. By joining points M and B, we divided the grain shape into two parts. We have the upper part, this is actually segment BUM, this is segment BUM, and the lower part, the second part, this is the lower part, is the lower segment BLM. So by joining points M and B together by straight line, we divided the grain shape into two segments. We have the upper segment BUM, and we have the lower segment MLB. This is the lower segment MLB. And we calculate the area of each segment separately, and then we add the areas of two segments together, and this will be the area of the grain shape. So first of all, we calculate the area of the lower segment BLM. In order to find out the area of this lower segment BLM, I copied sector BAM in an Olympiad and analyze this sector BLM. So actually, this is sector ABM. So it's actually sector ABM. This is sector ABM that I copied from the original domain. In sector ABM, this is again 2 alpha. This is equals to 53.13 degrees in its size. AB equals to AM equals to 10, the above the radii of the quarter circle, this is equal to 10. So this is sector ABM. What is the definition of a sector? A sector is a portion of a circle enclosed by two radii and the arc between them, arc BM. This is sector AOB. You can see that the green sector AOB is a portion of a circle enclosed by two radii, this is the radii of the circle, and RKB between them. The two radii defined as the legs of the sector. Angle theta is the angle between the legs of the sector. And the area of this sector, the green sector AOB, equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. I repeat again. A sector is a portion of a circle enclosed by two radii and the arc between them. And the area of any sector equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. So the area of this sector equals to pi r squared times theta over 360 degrees. So we use the new formula in order to find out the area of this sector A and B. The area of sector A and B will be equal to, according to the formula that I presented to you now, the area of this sector A and B will be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the circle, that is 53.13 degrees, over 360 degrees. R is 10, therefore r squared is 10 squared, that is 100, so pi r squared is 100 pi, times 51.13 degrees, over 360 degrees. In total, the value of this expression, 100 pi times 53.13 over 360 degrees, is equal to 46.3646 square units in size. So in total, we should find out that the area of this sector ABM equals to 46.3646 square units in its size. Our task is to find out the area of the lower segment BLM. This is the lower segment BLM. We have to find out the area of the lower segment BLM. From the drawing, it is very easy to see that the area of this lower segment BLM equals to the area of sector ABM minus the area of triangle ABM. Again, the area of sector BLM, the lower sector BLM equals to the area of the lower segment BLM equals to the area of sector ABM minus the area of triangle ABM. it's very easy to see that if you move from the sector this triangle ABM, we get segment BLM. Okay, so there of segment BLM equals to there of sector ABM minus there of triangle ABM. We already found out that there of sector ABM equals to 46.3646 coordinates in size minus there of triangle ABM. I presented to you a new formula that will help us to find out the area of any triangle. This is triangle ABM, that could be any triangle. In triangle ABM, side AB equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta. So there of this triangle ABC, that could be any triangle, equals to A times B, that is the multiplication of the two sides by each other, times sinus angle that is between the two legs, the two sides, that is theta over 2. So repeat again, there of this triangle ABC, that could be any triangle, equals to A times B times sinus theta over 2. We use the new formula in order to find out the area of this triangle ABM. According to the new formula, the area of this triangle ABM will be equal to AB times AM times sinus the angle between the two sides, that is 53.13 over 2. Repeat again, the area of this triangle ABM equals to AB times AM times sinus 53.13 degrees over 2. AB is 10, AM is also 10, so AB times AM is 10 times 10, that is 100. Sinus 53.13 degrees is 0.8 divided by 2. 100 over 2 is 50, and 50 times 0.8 is 40. So in total, we found out that the area of this triangle ABM equals to 40 square units in size. And the area of this segment BLM equals to the area of sector AMB, that is 46.3646, minus the area of this triangle ABM, that is 40 square units. 46.3646 minus 46.3646 square units in size. So in total, we found out that the area of this lower segment BLM is equal to 6.3646 square units in size. So we have to find out the area of the upper segment MUB. The area of this upper segment MUB. In order to find out the area of this upper segment MUB, I copied sector MOB in an operator to analyze this sector MOB. This is sector MOB. So actually, this is sector MOB that are coming from the original drawing. The angle between the legs of the sector is equal to 2 beta, that is 126.87 degrees in its size. OM equals to OB, they are both the radius of the same circle, that is equal to 5. So according to the formula that I presented to you, the area of this sector OBM equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 126.87 degrees over 360 degrees. R is 5, therefore r squared is 5 squared, that is 25, so pi r squared is 25 pi times 126.87 over 360 degrees. So in total, the value of this expression, 25 pi times 126.87 over 360 degrees, it is equal to 27.678 square units in size. So in total, we should know that the area of this sector OBM equals to 27.678 square units in size. Our task is to find out the area of the upper segment BUM. This is the upper segment BUM. You have to find out the area of this upper segment BUM. From the drawing, it is very easy to see that the area of this upper segment BUM equals to the area of sector BUM. This is sector BUM minus the area of triangle BUM. Minus the area of this triangle BUM. It is very easy to see that if you move from this sector BUM, this triangle BUM, we will get this segment BUM. So the area of segment BUM equals to the area of segment, the area of sector. The area of segment BUM equals to the area of sector BUM minus the area of triangle BUM. We already found out that the area of sector BUM equals to 27.678 degrees in its side minus the area of triangle BUM. What is the area of triangle BUM? according to the formula that I presented to you a couple of minutes ago, that triangle BOM will be equal to MO times BO, or BO times OM, times sinus the angle between those two sides, that is sinus 126.87 degrees, divided by 2. BO is 5, OM is 5, so 5 times 5 is 25. Sinus 126.87 degrees is 0.8 divided by 2. 25 over 2 is 12.5. 12.5 times 0.8 is 10. So in total we should know that the area of this triangle OBM equals to 10 square in size. So in total the area of this upper segment BOM equals to the area of sector BOM, that is 27.678 degrees in its size, minus the area of triangle BOM, that is 10. 27.678 minus 10 is 17.678 square inches in size. So in total we should know that the area of the upper segment BUM is equal to 17.678 square inches in size. So the area of this upper segment BUM is equal to 17.678 square inches in size. And we have found out that the area of the lower segment BLM is equal to 6.3646 square inches in size. And therefore the area of the green shape equals to the area of the upper segment BUM, that is 17.678, plus the area of the lower segment BLM is equal to 6.3646 square inches in size. And again, the area of the green shape in total equals to the area of the upper segment BUM, that is equal to 17.678, plus the area of the lower segment BLM, that is equal to 6.3646 square inches in its size. And 17.678 plus 6.3646, in total it is equal to 24.0426 square inches in size. So in total we found out that the area that you are looking for this question, that is the area of this green shape, is equal to 24.0426 square inches in its size. Okay, thank you very much.